Hey guys, here's 3.6 projectile motion. Let's get started. Okay, so whoa. Asking the first question here. Calculate the horizontal and vertical components of the vector. Okay, so if you don't remember how to do this or you want some refresher, go back to your chapter 2 of the vectors and you can look over them there. But let's walk through it here. So remember, a vector can be anything that has direction and magnitude, right? So velocity is a vector, acceleration can be a vector, force. There was several things that I had you guys determine or memorize that were vectors. And I gave you questions where I gave you a magnitude, so 30, and I gave you a direction, in this case the 25 degrees. And I asked you to break this up into a vertical and a horizontal component of the vector. Yeah, and so if you remember, let's kind of walk through it here. Um, uh, you can act like it is a triangle, right? You can act like it's a triangle, and the vertical component is right here, and this is the horizontal. Okay, and so if you look at it, this is your degree, right? And this is your opposite. If you remember all this, this is your adjacent and this is your hypotenuse, right? And then to go about calculating, like let's say you want to calculate this, we'll call the horizontal portion y, and we'll call the I saw the vertical portion y, and we'll call the horizontal portion x. Okay, so let's say you want to calculate it. So you want to calculate the y value. And some people forget about this. That 30 is your hypotenuse. Okay, that 30 is your hypotenuse. Okay, so you would use your SOHCAHTOA, right? SOHCAHTOA. And then here what you have is you have your hypotenuse, you have an angle, and if you're looking for your opposite, you're looking for your, if you're looking for your vertical component here, y, you're looking for the opposite, right? So you you're looking for opposite, you have hypotenuse, that's right here, that's so, right? So on this one it would be sine of some angle, which in our case is 25. Here, you know what? I'll even put 25 already. So 25 is equal to opposite, which is the thing we're looking for, y, over hypotenuse, which is 30. Okay, and in order to solve for that, it'd be y is equal to 30 times sine of 25. 25. And you would just plug that in the calculator. Make sure that that is a degree, right? 25 is in degrees. So make sure that you're not in radians. If you are in radians, it tells you in the top right-hand corner, right? It says either DEG for degree or RAD for radians. And in order to switch that, it's document, so doc 72, and switch it to radians, okay? But let's plug that in real quick. 30 times sine of 25, and that comes out to 12.7. 12.7. Okay, 12.7. And remember, that is a vector, so it's still meters per second because this was meters per second. Okay, and remember, that was how you calculate the vertical, right? Now, you can go about using that SOHCAHTOA method in order to calculate anything. But if you remember now, I would hope that you remember, sine calculates verticals. And in order to calculate horizontals, it's cosine. So it's 30 times cosine of 25. Which in this case, here I'll do it real quick, 30 times cosine of 25, that comes out to 27.2. Okay, and so like let's say you're going to do this one, I ask you to break this one up. First, remember, your angle always needs to be to the horizontal. Your angle always needs to be connected to the horizontal or the x value. So like this one, I have it connected to the vertical, right? So I don't want that. In order for me to calculate it, you know, the vertical being the sine and the horizontal being the cosine, it needs to be connected to the horizontal line. So this would be 60 degrees, right? Okay, so if I want to calculate the vertical here, so the vertical portion, now remember I can draw this vertical portion on the side here. And think about y. Yeah, I drew it as a triangle here, right? I could draw this line right here, or I could draw this line right here. It's the same distance no matter what, right? That vertical component of it is going to be 12.7, whether or not it's drawn over there, drawn over here, drawn way over to the left. It doesn't really matter. It's still going to be 12.7. So if I want to calculate the length of that vertical right there, it would be 50, because it's your magnitude, your hypotenuse, times sine of your angle 60. Okay, and then so that's what this one would be. So that length would be 50 times sine of 60, and that would come out to 43. So this right here would be 43.3, and it would be meters per second. Yeah, 43.3 meters per second. And if you want to calculate that horizontal, it'd be 50 times cosine of your angle. And remember, that angle always needs to be from the horizontal. And you just plug that in and you get your answer, okay? So that's how you break them up, okay? That's how you break your vertical and your horizontal up, okay? So let's go into how you would draw the velocity vectors for this ball's motion as it flies, okay? So when you kick it, okay, now if you think about it, I mean, the velocity is going like this at a diagonal. You know, it's flying like this. Yeah? But what we're doing is we're breaking up the velocity vectors, and we always break them up into the two dimensions, the vertical and the horizontal. So like, let's say you kick it with some velocity that looks like that. Well, what you have is you have a vertical velocity and you have a horizontal velocity. Yeah? And if you can tell, I kind of try to match it up vertically and horizontally. That's what it should be. Okay, so I'm not going to ever ask you to draw this is called the resultant, right? And you use Pythagorean's theorem to get it. I'm not going to ask you to draw that. I always want you to break it up into two dimensions, okay? So you got your vertical and you got your horizontal. Okay, now remember, from the horizontal motion that we just did, nothing accelerates the ball horizontally except for when this person kicks it. It doesn't accelerate or decelerate as long as we ignore air resistance. So the horizontal velocity would always be the same. Always be the same. It would be like if it was kicked with a horizontal velocity of like 5 or whatever, it would be 5 the whole way. So make sure that when you're doing your notes here that you're trying to make all these horizontal vectors the same length. Okay? They're all the same length. Okay, we just got this last one here. My computer's going really slow. I don't know if you guys can hear it. It's like, sounds like it's going to explode. Okay, now I gave it an upwards velocity, right? Because when you kicked it, it went upwards with some amount of velocity. Now, what's going to happen to that velocity as it flies higher and higher in the air? Gravity is going to slow it down, right? Gravity is going to slow it down. So that velocity vector should get smaller as it flies in the air. Should get smaller and smaller until it reaches the maximum height. And what would be your vertical velocity up here? There wouldn't be one, right? Your vertical velocity at the top here, we'll call it like Vy for vertical. The vertical velocity at the top would be 0. There'd be no vector on top or bottom. There would only be horizontal. And that's important. Okay, that's important because if they ever ask you what is the velocity at the top of the path, well, the velocity is whatever the horizontal component of the velocity was. Yeah. So if your velocity, if you kicked it for like let's say 50 meters per second, let's say that's the velocity you kicked it with, at an angle of like 20 or something like that, some weird angle, 20 degrees. It says, what's the velocity here at the top? Well, the only velocity that you have here at the top is the horizontal, right? So you'd just be like, okay, well, if you want the velocity at the top, it'd be 50 times cosine of 20, right? And that would calculate your horizontal velocity because it's only the horizontal portion of it, right? If you wanted to calculate your verticals, that's going to be different. Okay, so it loses velocity going up, and then on its way down, it's going to gain velocity in a downward direction, right? Because gravity is making it go faster and faster as it falls. So these velocities should be getting bigger and bigger. And they should pretty much go the opposite of what these went. So I kind of tried to do that. All the lengths should be similar to what these were going up, but they should be going down. Okay, and then remember, acceleration throughout this entire thing is negative 9.8. Never screw that up. It's always the same. If a ball is in the air, gravity is the thing accelerating it downwards towards Earth. Okay, now how about we do an example here? I only got one example for us, and I got some graphs, okay? So let's walk through it. A ball was thrown into the air with an initial velocity of 43 meters per second at an angle of 60 degrees to the horizontal. If it was released with an initial height of 1.1, calculate how much time it was in the air for. Okay, so let's look at this. We got a person throwing a ball. Okay, they release it at some height here. That height is 1.1 meters. That is a vertical height, right? Remember, we're going to be breaking up our givens into a vertical and a horizontal table again. So you need to make sure to understand between your vertical stuff and your horizontal stuff. Now this ball flies into the air, right? Okay, and comes down and hits the floor, down at the bottom here. Okay. It was thrown with an initial velocity of 43 meters per second, and it had an angle to the horizontal that was what was it, 60? Okay, so there's my little drawing here. It's everything that was given to me, right? So it says calculate how much time it was in the air. Okay, so first thing you should be doing here is setting up your givens, okay? And you should separate them so you got your vertical givens and your horizontal givens. So, and remember, over here with the vertical, you can use the big three formulas. Yeah, so you got Vx equals V naught plus AT. You got your x equals x naught plus V naught t plus a half AT squared. And you got your Vx squared equals V naught squared plus 2a x minus x naught. Okay, so you can use any of those. But remember, on horizontal, there is no acceleration, so there's only one formula. It's velocity is equal to the horizontal distance divided by the time. Okay, and remember, the only thing that is the same in both of these is the time. So you could put that right here if you wanted. Time is always going to be the same. So if you calculate time in one of them, you got the time in the other. Okay, so first thing it says is calculate how much time it was in the air. Okay, well, let's write down all our givens here. Horizontally, I know the velocity is it's like 43 meters per second, but it's at a 60-degree angle. So what's my horizontal velocity? Well, that's why we did the components, right? So you got this vector of 43 meters per second, and you have it at an angle of 60. So to get your y velocity, here I'll call it the y velocity like that, and to get your x velocity, you just multiply by the stuff that you have. So 43 times sine of 60. And here, 43 times cosine of 60. Okay, and that will give you your horizontal and your vertical velocities. So let's calculate what that is. 43 times sine of 60 is going to be 37, and 43 times cosine of 60 is 21.5. Okay, so this one is going to be 37.2, and this one will be 21.5, and they're both meters per second, okay? So I can write those down. I know those now. My initial velocity vertically was 37.2. And my initial velocity, or its only velocity, it's not even an initial because it never changes, right? It's always 21.5 because horizontally it doesn't change its velocity. There's nothing accelerating or decelerating it. Okay, so now we did that. That was the whole new component. Everything else should be the same, okay, from what we've been doing. So our initial position vertically was 1.1. Vertically, gravity was the thing making it move, right? Down and up. Calculate how much time it was in the air. Well, that means we want to figure out when the position, the final position, right, is equal to 0. That's what we want to do. So I'll put that right here. So we want to find out when our final position is equal to 0, because that'll tell us how long it was in the air, right? And am I missing anything? I don't think so. I think we're good. Okay, and then horizontally, I think that's everything that we have as well. Okay, so calculate how much time it was in the air. Well, let's use our vertical stuff and look at the formulas here and see which formula would be the easiest. And I think the easiest formula is going to be x equals x naught plus v naught t plus a half at squared. Okay, so our final position is 0. Our initial position was 1.1. Plus our initial velocity was, what was it? 37.2. Because it's the vertical initial velocity, right? We don't want to get the vertical and the horizontal stuff mixed together. Times time plus a half. Acceleration is negative 9.8 because it's gravity moving it vertically times t squared. Now guys, if you're going to try to solve that by hand, you'd have to use quadratic equation, the quadratic equation. I personally don't want to mess around with that. So I would just go over to my calculator and do the solver. So go algebra, solve, okay, algebra, solve. And then I think we've done this enough that you guys are probably pretty good at it. Is 0 equals 1.1 plus 37.2 times x plus, whoops, times x plus 0.5 times negative 9.8 times x squared and comma x to solve for x. And I got two answers. Remember, it is always going to be the positive answer, 7.6. So t is equal to 7.6. If you want to be more direct, 7.62 seconds. That's how much time it was in the air. And remember, when you calculate that, that is nice because it gives you the answer to two sides, right? It's the only thing that crosses dimensions is time. Okay, calculate the ball's range. So how far did it go? Range means how far did it go horizontally? Well, you just come over to our horizontal thing. There's only one formula to use, so you don't really have to decide between anything. And you have two of the things you need. If you were lacking time, you would have to come over here and solve for time, right? But we have the two things that we need, so calculate the ball's range. So I got v equals x over t. Well, if I want to solve for x, I would multiply by t on both sides, right? So my distance is going to be equal to, my horizontal distance will be equal to velocity times time, which should be a pretty simple thing to do here. It's just going to be the velocity. Now remember, it's only the horizontal velocity, because that's what we're talking about. It went 21, the horizontal velocity was 21.5. We're going to multiply it by the time, which was 7.62, because that's how long it was in the air for, right? So 21.5 times 7.62. Okay, that's going to give me an answer of 163.83. 163.83. And that's going to be in meters. There you go. Okay, that's how far it went horizontally. So if you wanted to write that now into here, you could. Okay, so calculate the ball's max height. Okay, so max height would be up here, right? That's going to be your max height. So when you come back down here, you want to make sure that you're realizing all this isn't going to be the same. The time, 7.62, was to go up and back down, so I can't use that time, right? And then the final position I used here was 0, which it's obviously not at 0. It's at a highest point, right? But one thing we do know about this ball at this height is that the velocity was 0, right? We know the vertical velocity was 0. And we do know the initial velocity here, vertically, was 37.2, right? So it looks like if you just focus on vertical stuff, okay, one thing that you know is your initial velocity was 37.2. You know your final velocity was 0. You know, vertically, your acceleration was negative 9.8. And wants to know how much or what was calculate the ball's height. So it's looking for this, right? And we know our initial height was 1.1. So it's looking for our final height, right? Well, given those things, I don't need to worry about any horizontal stuff because horizontally is not going to tell me how high it went, right? That is a vertical thing. So I can use, it looks like this equation right here would probably be the easiest. The final velocity squared equals the initial velocity squared plus 2a x minus x naught. Yeah, so just plug in all our stuff here. So we got the final velocity was 0 squared equals the initial velocity was 37.2 squared plus 2 times negative 9.8, and then x minus 1.1. And we're just solving for x, right? You can do that on a calculator. There's no reason to do it by hand. Oh, I don't know why I put a question mark. I'm going to solve for it. So x is going to be equal to, here, I'll do it real quick. Algebra solve, and I'm just going to do this. 0 squared equals 37.2 squared plus 2 times negative 9.8 times x minus 0. And then I want to go outside of that parentheses there and put comma x. And I get an answer of, the max height was 70.6. So it went 70.6 meters into the air, right? That was the vertical height that it went. Okay, so we do know some of our stuff here. Yeah, let's do a couple of the graphs. Now remember, there are two graphs, and this is everything I have, and we're done. Okay, there are two graphs because there is a horizontal graph and a vertical graph, right? I usually like starting with the vertical graph here. Okay, so let's talk about what's happening with the vertical graph. It started at some height, 1.1 in our case. Yeah, we can put, if it ever asks you to label stuff, you want to label everything you know here. So I know this is 1.1 meters, right? And then it went up into the air, and my pen draws like slower than I'm actually drawing, so I'm going slowly so I don't miss stuff. And it hits the ground, right? Oh no! My pen kept drawing. It should stop right there at 0, right? And the max height we actually know because we just calculated that. So if you wanted to label it on here, you could. I think it is, what was it, 70.6? So you can put 70.6 right there, meters. Okay. The velocity, remember vertically it started with a velocity. Vertically it started with a velocity of 37.2, right? So we need to make sure that it starts at that vertical velocity, 37.2. You can make a mark of what it was, right? And then it is going to decrease down to 0, right? That's at the max height right here. And then it's going to keep decreasing, right? And this line should be straight. I'm trying my best. And you could put how much time it was in the air for right here. It was 7.62. I know it stops right there because that's when it hits the ground. And remember, always take note, the slope is equal to gravity. Yeah. And then your acceleration time graph should be pretty simple. It's just a flat line because it is gravity, right? So it's negative 9.8 meters per second squared. Okay, and then don't forget your units on all these. I'm just kind of going through it a little fast here, so I'm not putting them all everywhere. Okay, horizontally. Okay, I usually like starting with my velocity one here, but you can start wherever you want, really. The velocity, remember the velocity is 21.5, and it doesn't change. It doesn't change, it's 21.5. So you would just put a dot there, make sure your velocity is unchanging. That line should be flat, okay? But it's 21.5 meters per second, right? And then you could put the time, it stops at a time of 7.62, right? Okay, the acceleration. Well, remember the velocity doesn't change, so there is no acceleration. So it just goes there. It stops at 7.62 as well, seconds. And then your position. So since it's always traveling at 21.5, that means it starts at 0. We can call this position here 0 horizontally, and it's going to travel to its maximum range, which was 163.83. So, and it will do that at a linear rate because the velocity never changes. So it's the slope here, something you should take account of. The slope here is equal to 21.5 because that's what the velocity was. The slope should be equal to velocity, right? The derivative of position is velocity. And you can make a mark of how much time it took, 7.62. You can make a mark of how far it went because it's talking about the distance, so 160, what was it, 163.83, yeah? 163.8. And there you go. There are your graphs. That's everything.